An integral domain is a commutative ring with unity and no zero divisors. A commutative ring is something in which if we take any two elements A and B in B, then AB should be equal to BA. Secondly, unity should exist. Unity in the sense E dot A equal to A dot E equal to A for all A in B. That is, over here E is the unity. And no zero divisors means if we take any two elements in the integral domain D, then AB should be equal to 0, then either A is equal to 0 or B is equal to 0. Okay, now we'll go to the Euclidean domain. So a Euclidean domain is basically an integral domain D if there exists a function D from D. D is the integral domain D minus the singleton 0 to the natural numbers union singleton 0 set, such that D of A, the function D of A is less than or equal to D of A into D of A B for all AB in the domain D minus singleton 0. Now if AB belongs to D and B is not equal to 0, then there exist elements Q and R in D such that A equals to BQ plus R, where either R is equal to 0 or D of R is less than D of B. The Gaussian ring is the ring ZI, which is equal to A plus iota B for A and B belonging to Z, is an Euclidean domain with valuation V, which goes from the Gaussian ring Zi to the set of integers defined by V of A plus iota B equal to A square plus B square. The ring of Gaussian integer is an Euclidean domain. So before proving this, we have to define a function V. So we'll define it. Now let Gaussian ring minus the singleton 0 set to natural number union 0 defined by V alpha equal to A square plus B square, such that alpha equal to A plus iota B belonging to Zi minus the singleton 0. Just take two elements from the domain. Okay, so let, which is equal to C plus iota D belong. Now what will be alpha into beta? Therefore alpha times beta will be equal to A plus iota B into C plus ib. That is equal to multiply the first term and this term, that will give you AC first into the second term of the second element. That is, now taking V of alpha times beta, that will be equal to, now V of this is defined to be A square plus B square. So this is our A and this is our B. So AC minus BD the whole square plus AD plus BC the whole square. That gives you A square C square minus 2 AC BD minus plus B square D square plus A square D square. So this terms get cancelled, plus A square D square plus B square C square. That is equal to theta not equal to 0, a non-zero element from the domain Zi minus singleton 0. Therefore, alpha upon beta, that will be equal to, alpha is A plus iota B and beta is C plus iota D. So that will be equal to A plus iota B upon C plus iota. That means we have to multiply the conjugate of this denominator with the numerator and also with the denominator. That will give you C minus iota D whole upon, this will get C square plus D square. So we can separate out the real and the imaginary parts of part of this. Will be AC plus BD upon C square plus D square plus I times BC. This is what I. This is BC minus BD upon take this as P and take this thing as Q. So we can write this as P plus IQ. We have simplified this thing and wrote it as P plus IQ. Where P is AC plus BD upon C square plus D square, and Q is BC minus AD upon C square plus D, with mod of F1 less than or equal to half and mod of F2 less than or equal to half. Now this mod is less than or equal to half. So if we shift M on this side, then F1 is equal to P minus M. So this implies that P minus M, the whole mod, which is equal to mod of F1, is also less than or equal to half. And similarly, this thing, Q minus M, this mod is less than or equal to, which is equal to mod of F2, which is less than or equal to half. Now, we have proved that alpha upon beta is equal to P plus IQ. Therefore, consider that alpha upon beta equal to P plus IQ. Okay, so that is M plus F1 and Q is M plus F2. So if we multiply both, so if we take P plus IQ, we'll get, what we get is M plus iota N into F1 plus iota F2. Just take beta on this side. What we get is alpha equal to M plus I N beta plus F1 plus iota F2 and beta. Consider this as Q and this as R, which is equal to Q is M plus IN and R is F1 plus I F2. Either R is 0 or E of R, E of this. So that will give you F1 square plus F2 square into C square plus D square. Is equal to 1 by 4 plus 1 by 4 into C square plus D square. This is less than or equal to half times C square plus D square. And this is less than C theta. Therefore, E of R is less than E of theta. Therefore, this satisfies the division algorithm, and hence Zr is a Euclidean domain.
Hello everyone, my name is Sia Naik, and today I will be doing the theorem. Prove that ring of integers z root 2, which is equal to set of a plus b root 2, where a comma b belongs to z, of the field q root 2 is Euclidean domain. Before starting, we need to prove that z root 2 is an integral domain. So first of all, we can say that z root 2 is an integral domain since the z root 2 is contained in R. Now, we use the norm given by absolute value of the field norm, which says that when your a plus root 2b belongs to z root 2, the norm of a plus root 2b will be equal to mod of a square minus 2b square. Then the map n from z root 2 to z, where z is greater than or equal to 0, is a norm on z root 2. Also, it is multiplicative. That is, n of xy will be equal to n of x into n of y. Now to show that n of xy will be equal to n of x into n of y. So we will take two arbitrary elements, x will be equal to a plus b root 2 and y will be equal to c plus b root 2. So this will be equal to n of xy. Using this property, we can prove that n of xy will be equal to a square c square plus 4 times b square d square minus 2a square d square minus of 2b square c square. Now to prove n of x into n of y. So from here we can see n of x into n of y will be equal to so n of x will be equal to n of x. Now, as we have already seen that n of xy will be equal to n of x into n of y, and since this norm comes from field norm of q root 2, the multiplicativity of n also holds for x comma y belonging to q root 2. Now to show existence of division algorithm. Once we say that division algorithm exists, then we can easily say that Z root 2 is an Euclidean domain. So therefore, to show, so by the division algorithm, if your integral domain R, if you want to prove that integral domain R is an Euclidean domain, then it means enough to prove that your A, B, Q, R belongs to R such that your A will be equal to B2 plus R. Then either your R will be equal to 0 or all of R will be less than your norm of B. Okay, now to prove existence of division algorithm, we will take two arbitrary elements x and y. These two elements in set root 2. Take x will be equal to a plus b root 2 and y will be equal to c plus d root 2, where your x comma y belongs to z root 2 and a, b, c, d, these elements will belong to z. Now your x by y will be equal to which will be equal to r plus 2 times s, where your r will be equal to ac minus 2 dv divided by c square minus 2d square, and your s will be equal to dc minus dv divided by c square minus 2d square. Now after this, we need to take an integer which is closest to r and s. So let n be the integer closest to r and m be the integer closest to s. So let n, therefore your r minus n will be less than or equal to half, and your s minus n will be less than or equal to half. Therefore the function t, which is equal to r minus n plus s minus n. Now from here, taking r minus n plus n. Now solving this, we will get this is t equal to x by y minus n plus n root 2. Now multiplying this y, we will get now here taking x on one side, we will get x will be equal to taking 0 to side of root 2. This will be your equation sum. Now here you can see that your yt is the remainder and your n plus n root 2 will be the quotient. So we have already seen that x will be equal to n plus m root 2 y plus yt, which is a star condition. And here we have already proved that your t will be equal to r minus n plus n minus m root 2. So from here we can say norm of t will be mod of r minus n the whole square minus 2 of s minus n the whole square, which will be less than or equal to r minus n the whole square plus 2 of s minus n the whole square. So this we can write is less than or equal to 1 by 4 plus 2 times 1 by 4, which will be equal to 3 by 4. We have seen that n of t will be equal to 3 by 4. For multiplicativity of norm, your n of yt will be equal to n of y into n of t. Here we have already seen that your n of t is 3 by 4. Therefore, we can write this as less than or equal to 3 by 4 into n of y, which is exactly in this form, where your n of yt will be less than or equal to 3 by 4 of n of y. So therefore, from here we can say that your n of yt will be less than your n of y, where in start we can already see that your n plus m notebook is your quotient and your y2